We will now understand about logical shifts. And we will particularly understand, well, I mean, there are two types of logical shifts. There is right logical shift and there is left logical shift. For now, we are only going to focus on the left logical shifts. What are these useful for? Well, left logical shifts allow computers to rapidly multiply a number with powers of 2. Okay, so think of all the powers of 2. You can this means that by using logical shift you can multiply a number with 2, with 4, with 8, right? These are all powers of 2, right? So you can multiply any number with any power of 2 using left logical shift. Now there are two things that you need to be careful about. So if you, let's say you write down the any particular power of 2, let's say 4, you should know what power of 2 you have to what powers you should give to 2 in order to have this number 4. Okay, so in order to have 4 you should have 2 raised to the power 2, right? Similarly, if you want to, let's say, have just 2, right, that's just 2 raised to the power 1, right? Actually, let me just write them down in a single line like this. What's the next power that we can write down? 2 raised to the power 3, that's 8. Then for 16 we can express it as 2 raised to the power 4, right? So these powers are going to be really, really important over here. Okay, what power does 2 have in order to make these numbers that you are going to multiply your given number in the question with? Okay, so let's say let's take an example. Let's say we have 80 and we want to multiply it with 2, for example. Okay, what power does 2 have? Well, since it's just 2 written over here, the power should be just 1, right? Just like this one over here, right? So the power of 2 should be 1 in order to give you 2, right? So we first the way we perform this is simply write down the binary representation of 80, which means it's going to be 64 and 32. No, 64, I mean 64 and 16, right? 32 is going to be 0, 128 is going to be 0, the rest of them are also going to be 0, right? So this is the binary representation of 80, right? Now and this is why it's called left logical shift. You take all the bits of 80 and you move them exactly one step to the left in accordance with the power of 2. Okay, because we just had to multiply with we are just required to multiply with 2 over here, so we will just move all the bits to the left, hence the name logical left shift, left logical shift. And how many steps do you have to move them one step to the left? Okay, so let's do that for each of these bits. Okay, so this one goes one step to the left, this one goes over there, this one goes over there. Okay, let me actually start copying these. So this one comes over here, this 0 is now written over here, this one is written in place of 0, and then over here what should we write down? We should be writing down this 0 over here, right? This 0 takes place of this 0, and likewise this 0 takes place of this 0. What about the place which was occupied by this 0? Well, if you have nothing in place of this 0, this just has a 0 over here, so it's like a filler value. Okay, what about this leftmost 0? I mean, We already have our 8 bits, right? What happens to this leftmost 0? It just vanishes. Okay, it gets deleted because there is no place after this 0 to shift it to. Like like the registers are comes in set of 8s. Okay, there are 8 registers. After that leftmost 8 register, there is no place for the 0 to be shifted towards. Okay, so it just gets deleted. Okay, so the rest of the representation that we have gotten over here, this representation is actually, if you notice again, if you try to convert it into denary, 128 and then 64 and 32, if you add those two numbers together, that is exactly equal to 160, which is something that we were expecting as well, right? So we got the exact binary representation for 160, which is the result of multiplying 80 with 2 by simply following logical shifts. So the computer would do exactly this thing. If you try to multiply a number with 2, it would simply take all the bits, move them one step to the left, and whatever resulting binary representation it gets, that representation is meant to be the exact result of multiplying by 2.